Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Terr, and this is my continuing feature on the Math Lovers book. And we're finally up to the next section on group theory. This is section 6.3. Chapter 6 is on group theory, which is a very big subject. That's why I'm spending a lot of time on and discussing a lot of different kinds of groups. But at least for now, we're done with finite groups. Now I'm going to start talking about infinite groups. And like I think I said when I first started talking about group theory, groups can be either finite or infinite, and they're both equally important. And we're going to see a lot of really interesting examples of infinite groups now. So today I'm just going to give you a little introduction to what infinite groups are like. Um, like I said, they're groups, but they have infinite cardinality, and they just obey the four axioms of group theory, namely, they're closed with respect to whatever group multiplication operation we're given, meaning that if A and B are two elements of the group, then their product has to be. And then they're also associative, so if A, B, and C are elements, then it doesn't matter how we group the terms. A times we could multiply B and C first, and then multiply by A, or we could take the product A times B and multiply that by C. We get the same thing. It doesn't have to be associative though. If it's associative, we call it an abelian group, but not all groups are abelian. As a matter of fact, we looked at several examples that aren't. And then the other two axioms, identity. Every group has to have an identity element. That's true of infinite groups as well as finite groups. And finally, every element has to have an inverse, meaning that if A is an element of your group, there has to be an element which we call A inverse, which we write with a superscript -1, like A to the power -1. That just means A times A to the power -1 is equal to A to the -1 times A, and that's equal to the identity. So if it satisfies all four of those axioms, then it's a group, whether it's finite or infinite. And today I'm just going to give you some very simple examples of some infinite groups. It turns out a lot of the number systems you've learned ever since you first learned about numbers turn out to be groups. You weren't told what groups were, but you already know a lot of groups without even realizing it. For instance, the integers with respect to addition. Remember, it's not enough just to specify the set you're working with. You also have to specify the group multiplication operation. And remember, I think I also mentioned the group multiplication doesn't have to be ordinary multiplication; it could be addition. So if we consider the group of integers, just the positive and negative whole numbers, which I'm sure you're all familiar with, and we let the group multiplication be just ordinary addition of integers, it turns out that this is a group. And how can we see that? Well, we just have to check that it satisfies all four axioms. So closure, if A and B are two integers, 3 and 5, for instance, 3 plus 5 is 8, that's an integer. Doesn't matter whether they're positive or negative. If you add any two integers, you also get a third integer. So it is closed. And then what about associative? Yeah, addition is associative. Not just of integers, but addition of anything is associative. So that one we get pretty easily. What about identity? Well, 0 turns out to be the additive identity element because you add anything to 0 when you get the thing you started with. 3 plus 0 is 3, minus 5 plus 0 is minus 5. You get the idea. You know, so 0 is the additive identity. What about inverse? Well, the inverse is just the negative. For instance, minus 5 is the inverse, the additive inverse of 5, because minus 5 plus 5, you get 0. So I think that's pretty clear. The additive group, the integers with respect to addition do form a group. And that's the first example. Before I get off of this, I think I want to say one more thing really quickly, though. You might wonder whether the integers are a group with respect to ordinary multiplication. Turns out they're not. The integers, the only way they would be closed with respect to ordinary multiplication is if every integer had a multiplicative inverse, but obviously they don't. For instance, 2. The multiplicative inverse would be the reciprocal. The reciprocal is what we call the multiplicative inverse of a number, and the reciprocal is 2 is 1/2. That's a fraction. That's not an integer. You have to multiply 2 by 1/2 to get the multiplicative identity, which is 1. So even though the integers are a group with respect to addition, they are not a group with respect to multiplication. Just thought I'd point that out. In order to make it a group with respect to multiplication, you have to go to the rational numbers. And I'm going to kind of jump the gun here a little bit. I don't talk about this in my book, but the integers are a type of structure called a ring. It turns out you can get different kinds of structures if you include both addition and multiplication. You can get rings or fields. And the integers, because they're not a group with respect to multiplication, they're not a field, they're a ring. Rings are not quite as, what's the word, robust as fields. Rings are kind of harder to work with, but there are a lot of important rings. Something a lot of abstract. Something you see a lot in abstract algebra, which is a pretty complicated area of math. But if you have two operations that are both algebraically closed, I mean they're both groups with respect to, except you can't include 0 for multiplication. So if it's a group with respect to addition, and it's a group, and all the non-zero elements form a group with respect to multiplication, then it's what's called a field. And it turns out that the integers are not a field; they are a ring, but the rational numbers are a field. I kind of jumped the gun here. Let's look at addition again. So let's show that addition is the rational numbers with respect to addition still form a group. Well, you take any two rational numbers, you add them, you get a third rational number. That's pretty easy. Sometimes they're not that easy to compute. You have to use a common denominator, but I think you guys all did this at some point. In middle school, you added fractions and you found that the result was always a fraction. You just have to take the least common multiple for the denominator. And so they are closed with respect to addition, and they're associated because, once again, addition's associative, doesn't matter what you're adding. In this case, rational numbers. What about identity? Yeah, again, 0 is the additive identity element because 0 plus anything is the thing you started with. Doesn't matter whether they're integers or rational or real or complex. So yeah, 0 is still the additive identity element. What about inverse? Well, again, the inverse is just the negative. It doesn't matter what you're adding. You take any rational number r, say 3/5. The additive inverse of 3/5 is negative 3/5. Pretty easy to see. So it is still a group with respect to addition. That was pretty easy. And then, like I was saying, the rational numbers also form a multiplicative group if you don't include 0. If you include 0, they're not a group because 0 doesn't have a multiplicative inverse. You can't divide by 0. But let's suppose we just consider the set of all non-zero rational numbers of the form a over b, where b is non-zero, a and b are both non-zero. Well, let's see if that's a group with respect to multiplication. Well, is it closed? Yeah, if you multiply any two rational numbers, you always get a third rational number. In this case, it's a lot easier to compute. A over b plus c over d is ac over bd. I think you learned that a long time ago. You just multiply numerators and denominators. So it's easy to multiply two fractions. It's not so easy to add them. What about associative? Again, multiplication is associative, just like addition. So we kind of get that one for free. What about inverse? Well, this time the multiplicative inverse of a number is 1. I mean identity. I'm sorry. So the multiplicative identity is 1. Because that anything times 1 is the thing you started with. So yeah, 1 is a rational number. Multiply any other rational number r by 1, you get r. So yeah, 1 is the multiplicative identity. And what about inverse? Well, inverse is just the reciprocal. So the inverse of a over b is b over a. Multiplicative inverse is pretty easy to see that a over b times b over a gives you ab over ab. If you simplify that, you get 1. So, so yeah, the non-zero rational numbers form a multiplicative group, and I just proved that the rational numbers form a field, by the way, because they're an additive group, and the non-zero ones form a multiplicative group. That makes it a field. Um, yeah, I think it's actually the smallest field of ordinary numbers. But then you've also got the real numbers and the complex numbers. These are also both fields, it turns out. Let's look at the reals again. You can use exactly the same arguments I used for the rational numbers to show that the real numbers are an additive group. I'm not even going to bother doing that. You can check it yourself. Um, and then if you do the multiplicative, you consider the non-zero real numbers with respect to multiplication. Basically, use the same argument I used for the rational numbers to show that that is also a group. So the real numbers are also a field, and they're a bigger field than the rational numbers. The rational numbers are what I call a subfield of the real numbers. Um, and then finally, I talked about complex numbers in chapter 4. Complex numbers turn out to be a third field. Um, Maybe I should just go over this one because complex numbers are a little more complicated. So let's first show that the complex numbers form an additive group. So remember what a complex number looks like? A plus bi, where a and b are real numbers, arbitrary real numbers. So suppose where you had two complex numbers, say a plus bi and c plus di. Well, if you remember from chapter 4, we know how to add two complex numbers. We just add the respective real and imaginary parts. So that will give us a plus c plus b plus d times I. So that is another complex number. That shows that the complex numbers are closed with respect to addition. What about associative? Yeah, complex numbers are associative too. I think I showed that in chapter 4. I'm not going to go over that again. It's just the real and imaginary parts are associative. That makes the whole thing associative. What about identity? Once again, 0 is the additive identity element for the complex numbers because if z is any complex number, 0 plus z is z. Remember, 0 is just 0 plus 0i. So you're just adding the real parts and the imaginary parts, and 0 is acting like the additive identity for both of those parts. And so it's the identity element for all the complex numbers. And what about inverse? Well, once again, the negative. The inverse, the additive inverse of a plus bi is minus a minus bi because you're adding the respective real and imaginary parts. Minus a plus a gives you 0. Minus b plus b gives you 0. So if you add those two, you get 0. So that proves that the complex numbers form an additive group. What about the non-zero complex numbers? Do those form a multiplicative group? Turns out they do. I think I gave you formulas for how to multiply and divide complex numbers, and I think you'll remember that when you multiply any two complex numbers, you always get a third complex number. Um, get a pretty complicated formula for it, but there is a formula which I don't want to state right now. Well, I guess I might as well. Suppose you're adding multiplying a plus bi times c plus di. You can use FOIL. Turns out you get the real part's ac minus bd, and the imaginary part is ad plus bc. So you get ac minus bd plus I times ad minus. I didn't say that quite right. Yeah, I times ad minus plus bc. So that is another complex number that shows that they're closed with respect to multiplication. What about associative? Once again, complex multiplication is associative. I think I proved that. I'm not sure if I proved that, but it is true. Um, Not too hard to prove in terms of the associativity of ordinary multiplication. And then what about identity and inverse? Well, 1 is once again the multiplicative identity of the complex numbers. That's not too hard to show. 1 times z is equal to z for any complex number z. And the multiplicative inverse, that's 1 over z. There's a formula for that. If z is a plus bi, I think it's a minus bi over a squared plus b squared. You take the complex conjugate divided by the norm, and that gives you the multiplicative inverse. So yeah, so that I just proved that the non-zero complex numbers form a multiplicative group, and that makes the complex numbers a field. Very powerful field, and it's a field with a lot of I like the complex numbers a lot better than the real numbers, even though in the real world we don't live, we're not used to dealing with complex valued quantities. The reason I like the complex numbers better is, they're algebraically closed for one thing. There's the fundamental theorem of algebra, which I talked about at the end of chapter 4, that says that every polynomial has all of its roots in the complex numbers. That's not true in the real numbers. So they're a lot nicer to work with than real numbers. But anyway, that completes my video for today. Introduction to infinite groups. We'll see a lot more examples of infinite groups. As a matter of fact, after this, I just talked about like groups of numbers, but we're going to talk about, more concrete groups. We'll talk about things like wallpaper groups and crystallographic groups, and we'll have a lot of fun with that. So anyway, that completes my video for today. So thank you for watching. Long live math, and I'll see you guys next time. Bye.